Okay, let's talk about shocks, and in particular, we're going to look at a normal shock. Okay, so shock waves are pretty cool. All right, they show up when you start going supersonic speeds. Okay, and they're an abrupt change in a fluid property. Okay, when you have an airplane going at supersonic speed, it, like we talked about before, like this, if as the airplane is moving in the air, there are signals going upstream to tell that fluid to move out of the way, right? And they move at the speed of sound. If you're going faster than the speed of sound, there's no communication. So when that airplane is flying at supersonic speed, anything in front of them has no idea what's going to happen until they pretty much hit them. Okay, and that's when a shock wave shows up. Okay, and what happens across the shock wave is you get an increase in pressure, you get an increase in temperature, density. However, your velocity will significantly decrease. It will be subsonic. Okay. So let me just show you. So here is, just say, a pipe, and we have an abrupt change, which is a shock wave. Okay. You can also kind of do this sort of in an airplane, but usually they're oblique and they're at angles, and but it's the same principle. Okay. Could be the nozzle that I just talked about as well, right? We get a normal shock wave. So I'm going to look at three equations: conservation of mass, pretty much momentum or forces, and then energy, to show you where equations across these shock waves come from to figure out what is the Mach number, what is the temperature, what is the pressure. Okay, so here is, we have the flow. So the Mach number 1 is greater than 1. V1, P1, rho 1. Here we have V2, P2, rho 2, and the Mach number 2 is less than 1. It's subsonic. Okay. So just to let you know, on this side, P2 will go up, V2 will go down, T2 will go up, the density goes up. Okay, so it heats up across the shock. So let's look at first, get to my pages here, conservation of mass across this shock. We always know that the mass flow rates are always the same. Okay, mass flow rates conserved. So we have rho 1 A1 V1 will equal rho 2 A2 V2. And we're looking right on the shock. So that's our control volume. And the areas are the same. So we get rho 1 V1 equals rho 2 V2. Okay. Leave that there for now. Let's look at momentum or forces. Okay. Momentum, forces. So let's draw a free body diagram. So here is the nozzle. We have a pressure force, P2A2, acting perpendicular to that. We have the other pressure force, P1A1. Okay. And then we have velocity coming in, right? I'll do in red, V1, and then leaving V2. So using linear momentum equation, sum of the forces equals MA plus summation of M dot V out minus summation of M dot V in. Okay, we can use that fundamentals to show an equation that relates pressure to velocity. Okay, so we're looking in the x direction only, so we'll do x positive that way. So P1A1 minus P2A2. This shock isn't moving in space, so that term is 0. The mass flow rate coming out is m dot 2 v2, and then coming in is m dot 1 v1. Okay. We know that the areas are the same, so I'm going to factor out the area. So P1 minus P2. And the mass flow rates are the same. It's a conservation of mass, so V2 minus V1. This is A, P1 minus P2. This is basically rho 1 A, V1, V2 minus V1. Or I could do rho 2A, A2, V2. Doesn't matter. Okay, just showing you that the areas are the same. So you end up with something like this. P1 minus P2 is rho 1 V1 V2 minus V1. Okay. Leave that here. That relates pressure and velocity. If you look up here, conservation of mass relates density and velocity. All right. And then the last one we're going to look at is energy. Okay, so dE of the control volume, dt, equals q dot net plus w dot net plus the summation of m dot h plus v squared over 2 plus gz. This is in minus summation of m dot h plus v squared over 2 plus gz, and this is out. This is 0, steady state. We have no heat transfer, no mechanical work. The elevation changes are the same. And so we end up getting is 0 equals 0 plus 0 m dot 1 h1 plus v1 squared over 2 minus m dot 2 h2 plus v1 squared over 2. Okay. Now, bringing that to the other side, the mass flow rates will cancel because they're the same. You end up getting this. H1 plus V1 squared over 2 equals H2 plus V2 squared over 2. And we can actually change this to be like CP1 T1 plus V1 squared over 2 equals CP T2 plus V2 squared over 2, because usually energy we're dealing with temperatures. Okay. Now, so we used energy, which relates to temperature and velocity. We use momentum, which is pressure and velocity. And then we also use conservation of mass, which is like a density velocity kind of combo. Why am I showing you this? Is because you could take those three, plug in more algebra, more equations, okay, and you'll end up getting equations like these that relates upstream Mach number to downstream. Okay, so this fundamental equation. This one here, okay, this is relating the downstream and upstream temperatures related to Mach number. Okay, and the last one is your pressure upstream and downstream related to Mach number. Okay, so each one set of those equations you can get to using a few more algebra, a few more equations. Okay, right? So here is the energy, right? This is conservation of mass. And here is your linear momentum or momentum forces. Okay. So I just wanted to show you how they're derived, and then we can use these three equations to figure out the relationships of normal shock waves. Okay, so what happens to the temperature, what happens to the pressure based on your upstream Mach number. Okay, so what I would like you to do is create this graph using those above equations and show me these relationships when you have an upstream Mach number difference from 1 to 10. Okay, this is a log plot, which you should be able to do to show these. Okay, and again, shock waves are important because we dealt with converging, diverging nozzles. Depending on your back pressure, which is if you're flying in the air, atmospheric pressure can drop, right? You could get a shock wave in your engine, and you don't want to do that. You want to know everything there is about shock waves so they don't show up. And knowing these equations, knowing how they're derived, is very important. Okay, I hope you enjoyed it. I hope it was a shocking revelation, and look forward to the next video. Bye now.